Hi. You can see we're in a new chapter. There's a nice comic. And so now we talked in the previous chapter about random variables, and you were building mass functions for discrete random variables. And chapter 5 just looks at some of the special cases of the discrete random variables. Um, I think of them like a story. Every random variable tells a story. In fact, I'm going to have to post for you. I have a nice sheet that summarizes the most important discrete and continuous distribution. So I'll have to send myself a note to remember to do that. That's a very helpful sheet. And anyway, let me go on from there. We're going to just start with, I think, maybe one of the most useful random variables that's discrete, the Bernoulli and the binomial. Um, well, like I said, it has a story, so I can tell you the stories of these different kinds of random variables. Probably the most basic random variable is called the Bernoulli random variable. Um, it was invented by one of the Bernoullis, a very famous family of mathematicians, and this random variable just takes on two values, either 1 or 0. It could be any two values, but it's either usually it's an experiment where you do something and you either have a success or a failure, and we're going to say P is the probability of success. So you can label however you want, but most of the time we say x equals 1 is a success and x equals 0 is a failure. And then the probability mass function is always just given by the probability x equals 1 is p, and the probability x equals 0 is 1 minus p, and that's a valid probability mass function. If you add up p and 1 minus p, it adds up to 1, and p is just the parameter of the probability of success, and we call this x a Bernoulli distribution. So it's a Bernoulli. A Bernoulli is you do something and you either have a success or a failure, and there's probability associated with each, and they add to 1. So this is very popular. Anything where you run pass, fail, yes, no, make, miss, defect, non-defective. So here's the most basic Bernoulli. Flip a fair coin. We'll let x equal 1 be a head, and we'll let x equal 0 be a tail. And so the x can only take on two values, 1 and 0, and probability is half and half. The mean of this random variable would be 1 times a half, 0 times a half, so it's a half, which makes sense. On the long run, you should expect about the same of both of them. I just wanted to show you not all Bernoullis are 50-50. At Ohio State, we could take classes pass-fail, and pretty much if you showed up, you're going to pass a course. But the probability of passing one of these courses, I'm going to label as 80%. X equal 1 is a pass, and we'll say x equals 0 is a fail. So the random variable x can either take on two values, either you pass or you fail, and 80 or 20%. It's a valid random variable, adds to 1. You could find the mean is 0.8. From a Bernoulli, we can build a binomial. So a binomial is really just n Bernoulli trials. So you do something n times and you count how many times you were successful. And p is the probability of success. It's always a number between 0 and 1. So there's, like I said, stories with every random variable. A binomial random variable, x, is the story of you do something n times, and out of those n times, you count how many times you were successful. There's only two choices. Either you're successful or you're not successful. P is the probability of being successful on each trial. It's constant, so that's not going to change. And the trials need to be independent. One outcome, one success shouldn't affect the next being a success, etc. So binomial is a story that I like to think of it as basketball for me. Free throws. A typical binomial, you go down in the gym, you have 10 free throws, your probability of success is 60%. You shoot 10, how many you make out of 10? And so you could make 0, 1, 2, 3, up to 10, and there's probability associated with each of those. So here's a binomial. X is, you buy circuit boards, the probability of defect is 5%, non-defect 95%. This might sound weird to you, but I'm going to let x be the number of defective boards in a sample of 3. So you can label a success anything you want. Here I'm making a success a defective board. Trials are independent. Every board you pick should be independent of the others. It's either defective or not defective. A success is actually having a defective board, so that's going to be 5%. And do we want to know how many are defectives out of the group we choose? So I'm counting how many successes out of 3. And there, it's kind of nice in class we built it by hand, but here is the binomial. For example, the probability x equals 0 defective boards means that 0 of them, that's too bad, 0 of them were defective, or sorry, yeah, 0 of them were defective and all of them were good, right? So notice up here, you have a difference. It'll be p to the x, 1 minus p to the 3 minus x. Either you're defective or not defective. If you put in 0, that means there were 0 defective and 3 non-defective. And I think most people get this part right here, the p to the x, 1 minus p to the 3 minus x. This though, we have to account for the number of ways that could happen. I mean, you're choosing 3 boards. You could have a good board, and then a bad board, and a good board, or you could have a bad board, right, and 2 goods, or you could have a good and a good and a bad. So there's like 3 ways you could choose one of them to be bad. So I have to, this accounts for the number of ways we could rearrange and get 3 or 1 defective out of 3 or 2 defectives out of 3, or that's why I need that binomial coefficient. So every binomial has this as their probability mass function. It's always going to take on this form. So that's what I'm showing you on the next page. This is the form of a binomial. It's always going to be probability of success to the x because I want x successes, 1 minus p to the n minus x because all the other ones have to be failures. I'm independent, so I can multiply these. And then out front, I have to see how many ways can I choose x successes out of n trials. The support always goes from 0 to n, always, 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 because you could have no successes all the way up to n successes. Again, think of basketball. You shoot 10, you could make none, 1, 2, all the way up to 10. And I'm just showing you the cumulative function. It's really just this mass function summed up to the value x. A lot of times I use this little symbol. X has the shape of or the form of a binomial. N is number of trials. P is probability of success. So we build a few in class. 20% of textbooks fail a binding test. X is the number of 4 that fail the test. So X here, failing is a success. And I want the mass function. So probability of here failing the binding test is a success. So 0.2 to the x, 0.8 to the 4 minus x. I could have all of them fail, none of them fail, anywhere in between. And I need that binomial coefficient out there to count the number of ways. I can verify for you this. I mean, p of x is always positive. There's nothing in here that would make it negative. And with a little trick from theorem 2.5 in the counting chapters, this sum right here, I'm going to use the binomial expansion, is equal to this by the theorem you see below, which is 1. What am I trying to show you? I'm trying to show no matter what you put in for n, as long as n is an integer positive and p between 0 and 1, this guy is always going to sum to 1, so we know he's always a valid probability mass function. So 5, I build another one. You can plug and chug once you get your p of x. You know, what's the probability there's 2 of whatever? Just stick in 2. What's the probability there's more than 1? Just stick in more than 1. So once you get your function, you just evaluate it at whatever values you're interested in. This is very nice. I mean, we know the definition for the mean of a random variable. We already did that in chapter 4. But now let's sub in, right here I'm just subbing in what p of x is for a binomial. And then I'm going to do some fancy stuff here. So a lot of this is just trickery to make it look nicer. I listed reasons over here. Here's all the reasons why I'm doing what I'm doing. But I'm just playing around to make this look a little bit nicer. You do enough proofs and you kind of know what you have to do. But the nice part of it is if I sum this guy all up and I'm just showing the mechanics of it, it's always going to sum to n times p. You don't believe me, put it in Maple. I'm not saying that's a great way to prove, but if you want to believe, that thing will always sum to n times p, and the variance will always be n times p1 minus p. So the expected value of a binomial is always n times p, which kind of makes sense. I mean, you shoot a basket 10 times, you go down and shoot 10 free throws, and you're a 60% free throw shooter. I expect you to make 6 shots. That's the expected value. And so from now on, if you know you have a binomial and I ask you the mean, you know there's a nice formula for it, and there's also a nice formula for the variance here. So down here, I just showed you a few. Here's a couple binomials, and if I ask you for mean and variance, you can always use, I mean, there's no reason you can't go back to the formula p of x. You know, I mean, that's the definition of expected value. You can always plug in your mass function times x and sum it over your x's, but it will always come out to be n times p for a binomial and n times p1 minus p for variance. There was just another example. Graphs, it's for different n's and p's. You can see what a binomial looks like. It's, again, not surprising. Like here, you do something 100 times, your probability of success is a half. Your mean should be sitting at 50. 50 trials, probability of success a half, your mean should be sitting at 25. So I think it's interesting to note, and we'll bring this up later, that a binomial, as long as n times p is fairly big, where big is around 10 or so, you will start seeing this to look very normal curve-like, which that's nice. We can estimate a binomial with a normal under certain conditions. If you took statistics, you might remember this, or you might have seen it. I love that. Yeah, things come out to be bell curves. I mean, you can see, I think I have one that isn't, and this isn't quite, and you can kind of see why. I mean, you only had 6 trials, probability of success a third, so notice your bell curve doesn't get to go all the way down because it can't, you can't take on a negative number of successes. So if you're not pushed far enough away from the x-axis, you're not going to get a nice normal curve. So if you multiply n times p, you get something like 2. You're not spread out far enough from the 0 to get a nice bell curve, but we'll bring that up later. And that's it for tonight.